Hello students, welcome you all. In NMR Spectroscopy, today I will explain population density or population axis and gyromagnetic ratio. In my previous lecture, I told you about the precessional frequency or Larmor frequency. Now, what do you mean by this population axis in NMR spectroscopy? Now, in my previous lecture of precessional frequency or Larmor frequency, I told you that when the precessional frequency of nuclei become equal to the frequency of radio waves, then absorption of radiation takes place and the nuclei will undergo transition from lower energy state to the higher energy state, and we get the NMR signal. What I am telling you, when the precessional frequency becomes equal to the radio frequency, then absorption of radiation takes place. After absorption of radiation, the nuclei will undergo transition from lower energy state to the higher energy state, and we get the NMR signal. So, but according to Boltzmann distribution, what this Boltzmann says that the number of nuclei in lower energy state is always slightly higher than the number of nuclei in higher energy state. So what this Boltzmann says, so according to Boltzmann distribution law, at 298 Kelvin, number of nuclei in lower energy state is slightly higher than number of nuclei in higher energy state, and this is due to small energy gap between these two states, due to small energy gap. Okay. Now, but if B naught, that is external magnetic field, is 1.41 Tesla, if external magnetic field is this much and temperature is 298 Kelvin, and in such case, in this case, N higher upon N lower means number of nuclei in higher energy state divided by number of nuclei in lower energy state. This is equal to, we can write, N upon N plus 9. Okay, so, or what it says, suppose N is 1 million. Suppose N is 1 million and this excess nuclei, this is equal to 9. So total number of nuclei in lower energy state and higher energy state, that is equal to 2,000,009. So out of 2 million nuclei, 9 nuclei are higher in lower energy state. So, or we can write out of 2 million nuclei, 9 nuclei are higher in lower energy state. Okay, in lower energy state. So now suppose what I mean to say, that if this is the lower energy state and this is the higher energy state, then always in lower energy state the number of nuclei that should be higher. in lower energy state, the number of nuclei that should always be slightly higher. Then only we will get the NMR signal. Suppose what happens if number of nuclei in lower energy state become equal to the number of nuclei in higher energy state. In such case, the energy difference will become zero and there would be no transition, and such state is called as the saturation. In that case, saturation occur. That is, when the number of nuclei in both energy state will become equal, then the saturation takes place and there would be no signal. Then no signal would be obtained in such case. Now, so also we know that according to Boltzmann distribution, we know that n higher upon n lower, this is directly proportional to e to the power minus delta E upon kT. This is the one of the relation. Also, this is, we can write, this is equal to e to the power this delta E. Delta is the energy difference between lower and higher energy state. So this is equal to h nu operating frequency divided by kT. Nu OP is the operating frequency of the spectrophotometer. So nu OP is the operating frequency of spectrophotometer, and this delta E is the energy difference between lower and higher energy state. Between lower and higher energy state. T is the absolute temperature in Kelvin, and K is the Boltzmann constant. Okay. So this is the according to Boltzmann distribution law. Okay. Now suppose if we open it, then this is equal to 1 minus delta E upon kT. If we open this exponential form, then this is equal to 1 minus delta E upon kT. We can write n higher upon n lower is equal to this much. Okay, so what this whole expression tells? This expression tells that suppose if nu operating increases, one thing, or we can write, suppose this delta E, if this is equal to 0, suppose if delta E is equal to 0, then n higher upon n lower, this is equal to 1 minus 0. This is equal to 1 minus 0. Or we can say that n higher, that is n higher, this is equal to n lower. Number of nuclei in higher energy state become equal to the number of nuclei in lower energy state. When it will happen? When delta E is 0. And when energy difference is 0, it means no transition will take place, and such situation is called as the saturation. So this is called as the saturation takes place. Saturation takes place and no transition will occur. No transition of nuclei occur. No transition of nuclei occur, or we can say no NMR signal will appear in such case. Now suppose what happened if operating frequencies increases. Suppose if we increase the operating frequency, and what will happen if we increase the operating frequency, or we can say after increasing the operating frequency, the delta E, the energy difference between two states, that will also increase. Delta E also increases, and if delta E increases, it means the N higher increases, or because this is 1 minus, this is equal to 1 minus, it means N lower, this is also increases, and lower number of nuclei in lower energy state increases. So as we increase the operating frequency, or then the number of nuclei in lower energy state increases. So this is called as the population axis. When number of nuclei in lower energy state is higher than number of nuclei in higher energy state, this is called as the population axis. This is called as population axis. Okay, and if excess number of nuclei are present in lower energy state, then we will get a good signal, and more is the excess nuclei, more will we get the good signal. So if N lower increases, then intensity of signal increases. Intensity of signal also increases. Intensity of signal increases. Okay, so that's why nowadays in modern instrument the operating frequency is always higher for the modern instrument. So for modern instrument this is always higher. Okay, now suppose so as the what I told you, as the frequency increases, the intensity of signal increases. So what we may say that, or we can say as the population, so as the frequency increases, number of nuclei in lower energy state increases, or the population axis increases. So you can see the table, the variation of population axis. Variation of population axis of proton 1H1 proton nuclei with operating frequency. So if you will see this variation, then let us see this variation. So suppose number of nuclei is suppose, or we can say if operating frequency is suppose operating frequency is 60 megahertz, or operating frequency it may be, suppose I say 80 megahertz or 100 megahertz, 200 megahertz, 300 megahertz or 600 megahertz. So it has been found that at 60 megahertz the population axis in lower energy state is 9. At 60 megahertz, what I have written here, so what I have written here, this is at 1.41 Tesla, and 60 megahertz, this 9 axis will be there in lower energy state. So 9 nuclei are present in excess amount in lower energy state. At 80, this is 12, and at 100, this is 60, at 100, this is around 16, at 200 this is 32, and at 300 this is 48, and at 600 this is 96 nuclei. So what you can see, at 600 megahertz operating frequency of spectrophotometer, 96 nuclei are present in higher amount in lower energy state. So that's why which spectrophotometer is good. This is the best spectrophotometer having the highest operating frequency, and such spectrophotometer are much expensive in comparison to here where the operating frequency is less. So this is about the population density and population access. Now let us come to the next one, that is the gyromagnetic ratio. Now, so what do you mean by this gyromagnetic? So I told you little bit about when we were discussing about this precessional frequency or Larmor frequency. Now let us see more about this gyromagnetic ratio. Now, so we know that when the absorption occurs, when absorption, or we can say during absorption of radiation, the frequency, the energy of radio waves become equal to the difference in energy of lower energy state and higher energy state. So when absorption takes place, when absorption of radio frequency takes place, so when absorption of radio frequency occurs, that is resonance occurs. When resonance occurs, in such situation, delta E, that is energy difference between lower energy state and higher energy state, this is become equal to the energy of radio frequency. This is the operating frequency. So when this becomes equal, then only the radio frequency is absorbed by the nuclei and transition takes place, and we get the NMR signal that I told you. So this, and we also know that as the magnetic field increases, B also increases. Magnetic field increases, then this delta E also increases. As the magnetic field increases, the energy difference between lower energy state and higher energy state increases, and we get good signal. So suppose if you see, then suppose this is the energy difference, and here the two nuclei are present, which are the degenerate nuclei. These are the two degenerate nuclei, and suppose these are the two degenerate nuclei, and after, as the external magnetic field increases, as this B0 increases, then what will happen? The energy difference between lower energy state and higher energy state increases. As you can see here, at this much B0, this is the energy difference. At this much B0, this is the energy difference. At this much B0, this is the energy difference, and like this. So we can see that as the external magnetic field increases, here the external magnetic field is equal to 0, where at this position the external magnetic field, we are increasing the external magnetic field, and delta E energy gap is increasing, and we will get the good signal, because in such case this energy state is more populated, the lower energy state that will be more populated. So what we can write, this delta E, this is equal to, therefore it is equal to mu, this is equal to H gamma upon 2 pi and multiply by mu operating. Okay, or we can say this H, this is equal to, B naught, or we can say this H nu operating, this is equal to H gamma upon 2 pi B naught. So H this will cancel out, or we can write mu operating, this is equal to gamma upon 2 pi multiplied by B0, or this gamma, this is equal to nu operating multiplied by 2 pi divided by B0. This is the value of gamma. Also, this is one of the relation. Also, this gamma or this magnetic moment, this is equal to gamma multiplied by Iz, where Iz, this is the magnetic, this is the angular momentum. So what we can write, this gamma, this is equal to nu upon Iz, or we can say gamma is the ratio of magnetic moment, and we are not going to discuss much more about this relation. So gamma is the ratio of magnetic moment to angular momentum. This is the another relation for this angular momentum. So gamma can be represented by either this relation, or gamma may be represented by this relation, and this gamma is constant. This gamma is constant for a particular nuclei. This is constant for particular nuclei. And the unit, if you see, then the unit is radian per second per Tesla. This is the unit for this gamma. Means at 1 Tesla magnetic field, what is the value of this gamma? That would be the that value is for a particular nuclei. So that at 1 Tesla, if B is 1 Tesla, and what is the resonating frequency there, what is the operating frequency where we get the signal, then we can get the gamma over here. So if you will see, then for proton, if you will see, then suppose if we know that if B is equal to, we have to put the B 1 Tesla, because we have to find the gamma is for per Tesla. Then if B is 1 Tesla and nu operating where the resonance occur, this is equal to 42.16. Then this gamma, this is equal to, gamma is equal to 42.16 multiplied by 2 multiplied by 3.14 divided by this 1 Tesla. This comes out to around 267.5 something. This comes. So this is the value of this proton. This is the value of this proton, which is the constant value for this 1 at 1 Tesla external magnetic field. Whereas if for, we say, for 13 nuclei, for C13 nuclei, if you find, if B is equal to 1 Tesla and this operating frequency is equal to 10.7 something, then if you find the gamma for this 13 carbon, and this comes out to be 10.7 multiplied by 2.314 divided by 1, this comes out to be, so this comes out to be how much? Around 2 multiplied by 3.14, 2 multiplied by 3.14, so this comes out to be around 60, how much? So 6.28 multiplied by this 10.7, so 10.7 multiplied by this, so this comes out to be around 65. This comes out to be around, we can say around 65, approximately. If you will see, it comes out to be suppose 65, around 65. So what we have seen, that for carbon 13, the gamma is very less in comparison to the proton. In comparison to the proton, gamma is very less for this. So gamma and we can see that this gamma is dependent upon this. Gamma is directly proportional to what? From this relation you can see gamma is directly proportional to nu operating, and then in turn it is directly proportional to the delta E. So as the operating frequency, if operating frequency is higher, then delta is high, gamma is also higher. Gamma is also higher. So gamma is the tendency of splitting tendency. This also tells about the splitting tendency. So gamma is also a splitting tendency. Gamma tells the splitting tendency also. Splitting tendency. So how? Because what we may see that here the gamma is only 65, here gamma is 267.5. So if we compare these two nuclei, if we compare the proton and if we compare the carbon 13, then if for proton the splitting, if splitting is like this for proton, if splitting is like this for this proton, then this is for proton, and for carbon 13 the splitting would be, this is the splitting for carbon 13 only. This is the splitting for carbon 13. So what we can see for proton, for 1H1, gamma for 1H1 is much higher than the gamma for 13. So it means the splitting is good, then the intensity of signal for this proton is also better in comparison to the carbon 13. At 1 Tesla, if we take 1 Tesla external magnetic field, in such case the intensity of signal for this proton, that would be better than intensity of signal for this carbon 13. So this is about the gyromagnetic ratio, and in my next lecture I will discuss about the relaxation process in NMR spectroscopy. Thank you.